Okay, so here's the question, the answer. You take the derivative of each component. Cosine 2t becomes -2 sine of 2t. Why? Because the derivative of cosine is the negative sine function. And then, of course, the 2 comes ahead by the chain rule. 2 comes ahead here for the same reason. Sine of 2t becomes 2 sine of 2 cosine of 2t. T simply becomes 1. All right, now when you evaluate, this is the derivative, by the way. And then you have to find the speed, which is based on the derivative at pi over 2. This is the notation I use. Lots of other people use this. Many other people actually don't use this. I think it's a great thing. So draw a long line, vertical line, and put the t value here. This means I'm evaluating this at pi over 2. Okay, so what's pi over 2? When you plug in pi over 2 here, it's a sine of pi, which is 0 times -2. That's 0. And then 2 times the cosine of pi, that's -2, isn't it? Because cosine of 2 times pi over 2, which is cosine of pi, is -1. So, all right, so this is the velocity vector of this motion described by r of t at t is equal to pi over 2, which is like 1.58 or something. All right, and so what is the speed? Well, that's just going to be the magnitude or the length of this vector, and that would be the square root of 5, whatever the unit that we are using is. All right, so that's the answer to this question. Okay, so let's quickly go into integrals. We will not do a lot of integration in this chapter, but this is, again, what you think it is. If r is your vector valued function, you know, xt, yt, zt, then you can define this definite integral, which is integrating r of t. I mean, it just means that you're finding the integral of each part. So this is the vector valued function where the first component is the integral of x. The second one is the integral of y. And the last one is the integral of z, all with respect to t. And so what does this mean? Well, if r is the velocity function, then the integral of r, you know, what does it mean? Well, it's got 3 components. This is the total displacement. Okay, so if you start here, and if the velocity is described like this, what you are doing here is talking about how much the object is moved. So it's pretty much the same thing as we had before. All right, so the last thing I need to mention, this is going to be a quick section, as I may have mentioned. It's this thing called the unit tangent vector. Okay, so here's the definition. Okay, so given the same vector valued function r of t, which is x, y, z. Okay, this part is also easy. All right, remember the I'll just say recall. This r of t is the velocity function. Okay, then the unit tangent vector. Okay, the unit tangent, what do you think this is? It's a tangent vector, that's the unit length, right? The unit tangent vector of r of t is, okay, so I need something that is tangent. Oh, by the way, the unit tangent vector is written as capital T. And by the way, try to differentiate, no pun intended, trying to differentiate between lowercase and capital letters. So this is T of T, but you know, T of T sounds weird. This is a capital T, and it's got the vector notation on top of it. So this means it's some special vector valued function, right? And this is, and we want this to be a tangent vector, which is v is a tangent vector, right? But in order to make this into a unit vector, we normalize it, okay? Or you can just call this r prime divided by the norm of r, same thing, right? And so if you normalize this, it's normalized velocity vector. If you do that, you basically have a the unit tangent vector, which is a bunch of you know, let's say if your motion is like this, and at each point it's a tangent, and the length is always 1. So at each point it's showing you with a unit vector which direction the object is moving. Okay, and so this is called the unit tangent vector. It is more important than you realize now. Okay, so as you know, the norm of this vector, not surprisingly, is always 1, okay, for all t. And that is a fairly important process. And in fact, I'm going to prove this for you. This is a theorem that we will refer to later, probably in section 4. And so if you don't get it right away, that's okay. We will not use it for 2 sections. But when the 2 sections, well, I will use one fact from this right now. But here's the statement. If r has a constant length, so let's say you have this vector valued function r of t, but at every t, the length of the derivative, or no, that's not the derivative. If the length of rt is constant, in other words, if rt has a constant length, let's say c, for all t, then the derivative is perpendicular to rt. So the velocity is going to be always perpendicular to that. And this is true for all t. Let me illustrate what I'm talking about, okay? So just a moment. Okay, so for instance, I have one 2-dimensional and one 3-dimensional vector value function example here. But let's say here, okay, so r of t is always on a certain circle of a certain length. Okay, so in other words, the object is like moving maybe counterclockwise. It doesn't matter, but the object is going around in a circular orbit. Okay, so at this point, it's here, and you notice here the tangent will be always like this, right? The tangent vector is absolutely going to be tangent to the circle. And so this will be t of t, okay? Actually, I should just call this the derivative. So the derivative is always going to be perpendicular. The blue is always perpendicular to the red vector, right? So that's what this is saying. Now here, a 3-dimensional vector, let's say this is constant, and the vector, all the vectors are sort of roaming around on this earth. Okay, so at this point, maybe it's here, and then moves to over here, moves to this point, you know, on the equator and so on. So the derivatives will be like here. Let's see, the derivatives will be like moving here, maybe moving here. It's always going to be perpendicular to that red vector. All right, so if r is a vector valued function where the length of the vector position does not change, then the derivative is always perpendicular to the vector that r defines. Okay. Now, again, there's one important and significant result that comes from this, but I'm going to go ahead and prove this for you. All right. So you should pay attention to this proof. Very cool. Okay. So we are given that the vector valued function always has the same length, right? In fact, r of t is equal to c for all c. That was my given. And since it's constant, oh yeah, so c, by the way, c squared is r dot r. You see that? Maybe I should be more specific here. Maybe I should write, come on, I need to erase this. I am not erasing any of this. That's the way to erase this. Okay, so this is r of t dotted with r of t, right? Okay, so that's that. Now differentiating, what do you get when you differentiate? If you differentiate a constant, you actually get 0. Okay, but this side, oh, that's a dot product of two vector valued functions. If you differentiate, it'll be r prime dotted with r plus r dotted with r prime. Okay, so this is one of those product rules that I talked about earlier. So you can go back in your notes, and there it is, number 4 gives you that. And assuming this is true, because there's a proof of it, you can apply it to that product, dot product. Okay, so this turns out to be just 2 times r dot r prime, right? Okay, this is still equal to 0. Now you can divide both sides by 0, and you, of course, come to the conclusion that r dot r prime is equal to 0. What does it tell you? Okay, that means r prime has to be perpendicular to, or in our new word, orthogonal to r. Okay, because that's what the dot product being 0 means. And so that's it. This tells you that, you know, these red and the blue vectors are perpendicular to each other. All right, so again, hold on to this. I'll tell you one thing before I finish. So here's, so what does it mean? What meaneth these things? What does this mean? Well, in particular, here's what we means. Remember T? Okay, this unit tangent vector, because of its name, and you can tell, it's always a unit vector, all right? So it's going to apply, the fact the theorem does apply to the capital T function, the unit vector function. The unit tangent vector has the constant length because we made it that way, okay? So that means, right, and this is something you should remember as we go into the next lesson. This means T is perpendicular to whatever we get when we find T prime. Okay, so T prime will be something perpendicular, and we will talk about what this T prime means next time. If you absolutely cannot wait to find that out, you can read ahead in the book, but I will explain what we do with T prime and what we do when you normalize T prime and what else you can do with T prime and T and so on. Lots of things are describable in terms of this capital T. So this capital T, the unit tangent vector for the vector valued function given, is going to be very important. In the next section, we will be talking about more of these related topics. Okay, so this concludes section 3.2. Section 3.3, the next section will be very important, and it's going to be very involved. It'll be longer than the first 2 sections. And so far we talked about the velocity, the acceleration, the speed, and the unit tangent vector. Taking off from that, in section 3, we'll be talking about the arc length, and then what is called the principal unit normal vector, and curvature, and binomial vector. So lots of things are coming up in section 3. All right, so until then, I hope you have a great day, and I'll talk to you later in section 3.3.